Welcome back. In this video, we're going to discuss fatigue stress concentration factors. Now these factors in the Shigley book use a K and a KF specifically. Now this can often get confused with the Marin factors. So we've already talked in the last video about Marin factors. The Marin factors adjust the endurance strength from the hypothetical endurance strength to the actual or to a more realistic endurance strength. And they always have the result of reducing the strength. So Marin factors like the surface factor, the size factor, and the loading factor, there's also temperature and several others that we don't use as often in this class, but all of these factors are going to be less than 1. So typical values might see 0.85, 0.75, case heat could be 1, or it could be a smaller number, 0.85, or the loading factor can be 1 depending if it's bending, or 0.85 if we're in axial load, so forth. But again, all of these have the effect of reducing a hypothetical endurance strength towards a more realistic endurance strength for our current loading situation. What we're going to be talking about in this lecture are stress concentration factors. And these stress concentration factors exist because the way fatigue failure works is by crack propagation, exactly like brittle failure. And anytime there is any sort of shape change that exists in our part, it's going to be likely that that is a spot where cracks are going to grow. So when you use a machine to drill a hole, or you use it to shape a fillet onto a shaft, there's going to be small micro discontinuities, and those are the places where cracks will tend to grow. So we artificially, with a fudge factor, which is our stress concentration factor, we artificially increase the magnitude of the stress. So the stress concentration factors look something like this, and I'm going to use again the analogy of water flowing in a stream. So if you imagine this stream here with a rock in the middle of it and the boulder, and there's water coming towards it, the water itself has to go around and gets a little jumbled up near the edges of this rock. Fluid flow, you'd have issues of turbulence and things like that. But for what we're concerned about is these certain areas here are areas where that flow tends to bunch up. And it's the same thing if we are talking about stress. So I've used this analogy before, but we end up with stress concentration areas. And the stress concentrates in these areas. Now recall for ductile failure, that was okay. We don't mind that the stress concentrates there because when it does cause those little tiny cracks to form, it ends up relieving some of the stress. And so we don't have as much of an issue with ductile failure. But for brittle failure, it was very important. Well, fatigue failure is that loading happening over and over and over again. And over time, you've got a part with maybe just the tiniest little inconsistency at some geometry change. And as we load this thing many times, that crack starts to grow. And as it grows, that stress concentration grows higher. So to account for the fact that anytime we have geometry change, so anytime you've got a hole, a fillet, a weld, pretty much any point that you can point out to on a shaft or a solid piece, and so okay, there's the hole, there's the fillet. Anytime you've got some geometry, there's going to be a stress concentration factor. So the stress concentration factor is a little bit different than when we were just looking at static brittle loading. We account for the hypothetical stress concentration factor. Recall from before, that was KT. This is our hypothetical stress concentration factor. It could also be called the theoretical stress concentration factor. And these come from the back of the book or online. In the Shigley book, they are listed under A15, and we'll look at those in a little bit. But it's the hypothetical stress concentration factor is basically a little bit high. So because of the ductile nature and because that's just a little bit of an overestimate, we end up reducing that hypothetical stress concentration based on how likely it is for that material to allow the crack to propagate. So we have this thing called Q in our notation that is called the notch sensitivity. And notch sensitivity is basically a material property. So over experimental data, they've come up with, for different materials, how likely it is that the material will be is likely to propagate a crack. And so we have empirical data for this, and we usually read graphs, and there's two in your equation sheet, one for normal stress and one for shear, and they read like this. The notch sensitivity is down here, and then the size of the notch is down here. So by notch, we mean the radius of a fillet or the radius of the hole. So we have a few experimental data, and the graphs basically look like this. There's a bunch of different lines. Each line represents a different ultimate strength, so this might be 100 kpsi ultimate strength. And then you find your size of the notch radius. Radius equals 0.1 inch. Millimeters is on the top of these graphs. And we're either looking for Q for normal or QS for shear. So the value of notch sensitivity is basically found by comparing the actual fatigue stress concentration factor to the hypothetical one and experimentally finding it from that way. However, we're not going to be experimentally determining our actual fatigue stress concentration factor, KF. This is what we're going to be computing. So KF is our fatigue stress concentration factor. So our notch sensitivity, hypothetical stress concentration, and fatigue stress concentration factor are all related to one another. So experimentally, Q is found through experiments by comparing the hypothetical one, KT, to the stress concentration determined from when the part actually breaks, depending on what material it's made out of. So that's how it's actually calculated. But what we want is to compute our value of KF. So more often we'll use this formulation where KF equals 1 plus Q times KT, our theoretical stress concentration factor, minus 1. This is for normal stress. And for shear stress, we will use KFS, which is the same one, but instead we're going to use the shear notch sensitivity and the theoretical shear stress concentration factors. So all of these values will take us from calculating our value of stress, our actual stress that we're going to use in our failure equations, as our KF times our computed stress. So this is how we would normally find stress, P over A, MC over I, multiply times the stress concentration factor to come up with an actual stress value, which is a little bit closer to what the part's actually going to be experiencing. Or the same thing for shear, the actual shear that we're concerned about, we can use KFS times the shear that we compute. So let's see how this works as an example. Say we've got a part that happens to match exactly one of our situations. Not always the case, but we'll fake it for now. This is a round shaft put under bending, M. So under some bending moment, M. And for completeness, I'll go ahead and use some values here. Let's say the large diameter here is 1.25 inches. The small diameter on the smaller end of the shaft is 3/4 of an inch, so it's 0.75 inches. And the fillet that I drew here so marvelously has a radius of 1/8 of an inch. So this is obviously not a complete problem, but it sets up our situation. So first of all, we can compute what would our normal stress be, our computed stress. So our computed stress, using the traditional format here, obviously we'd want to look at the smallest area right where the geometry starts to change. So that's this location right here, right at the beginning of the fillet from the smaller end of the stress. So we're going to say MC over I, or my over I, depending how you do it. And if this is a solid round shaft, we can make the, in this case, we can make the assumption it's 32 m over pi d cubed. That's the computed stress at that fillet location. Now we need to account for the fact that there is some geometry change which is going to cause stresses. So our first aspect is to find the theoretical stress concentration factor, the notch sensitivity, and the fatigue stress concentration factor. So we'll do those in parts. First of all, KT. This is going to come from the graphs. So you need to go to the appendix, or you can find some of these tables online. And we find the situation which matches ours. So hole in a plate is not correct. Hole in a plate and bending, notches in a plate, notches in a plate. This is a little bit more similar, but this is a rectangular filleted bar. And now we have the round bar. So this is our situation right here, where we've got a round bar with a fillet in underbending. So the things that we need is R over D, and to figure out which line to read, we need D over D. So let's calculate those. So R over D is 1/8 of an inch over 0.75 inch, or specifically 0.167. And D over D, the big diameter compared to the little diameter, tells us which line we're going to be on. And that, of course, is 1.25 over 0.75, or more simply, 1 1/3, 2/3. All right, so now we have the two things we need to read that KT graph. 1.667 is the line we should be on, and the notch size is about 0.167. Now what you'll find is that obviously doesn't match any of the lines that we have. So 1.67 is not the 1.5 line, but the next line is 3. So there's not much difference here between those two. So we can follow closely along with the 1.5 line. We're closest to that. Now the next value is the size of the radius compared to the diameter. So we'll find where we belong here. So we had 0.167, so that's pretty close to here. And you'll notice these values tend to clump up together. So we're more than likely somewhere stress concentration factor, if this is 1.6, maybe 1.5 is a healthy stress concentration factor. So from the graph, KT equals 1.5. Great. Now we need to know our notch sensitivity, Q. Well, this depends on the material that we're talking about. So let's pick a material. We can make it out of steel, since that's what our graphs are of. If we choose ceramics, then we're going to need to find our own new graph for that. But the steel I'm looking at has an ultimate strength of 170 kpsi. So now we can look at our notch sensitivity figures. So in order to find Q, we're going to need to look at the tables, or the figures. And in Chapter 6 of the Shickley book, there are figures 620 and 621 for normal and shear, respectively. So here's what the notch sensitivity equation looks like for normal stress. And you can see we have steels and aluminum alloys. So our steel was about 170, again, not on the line, but we're pretty close to the 150. So we can follow along that way. And now the size of our notch. So recall that it was 1/8 of an inch. So our notch radius was the size, is in this instance, the radius of the fillet. So what we need to do is find our notch radius, which is, as you recall, 1/8 of an inch. So 0.125, put us right about a quarter of the way here. And estimate that it's probably about a point right in here. So about halfway between, I think it's fair to call that 0.9. So obviously this is an approximate approach, not something that you're calculating exactly. So this is from the graph, and this is from the graph. And all we need now is to figure out what our fatigue stress factor is. So our fatigue stress concentration factor is 1 plus 0.9 times kT minus 1, 1.5 minus 1. So altogether, if you compute that, we get a Kf equal to 1.045. Notice this is pretty close to 1. So in general, our KTs, our hypothetical stress concentration factors, are almost always going to be greater and usually significantly greater than our fatigue stress concentration factors. So if you have absolutely no idea how to figure out your notch sensitivity for a material, say you don't have a table or chart for it, if you use just the hypothetical stress concentration factor, know that it's okay. You're just going to have a very conservative value. It's going to be a little high than it needs to be, but at least you're making mistakes in a more conservative direction. All right, so now let's put this all together. So our actual stress that we care about and we'll use in our stress concentrations will be Kf times our computed, or in this sense, it will be 1.045 times our computed stress, which we didn't give a value for m, but we can put 32 m over pi d cubed. So this is the actual value of stress that we would then go use in our failure equations. Now we could have done the same process if instead we had this bar, the same round shaft, with a torque applied. If we had the exact same round shaft, the only difference is we'd come up with a KTS and we'd come up with a QS. And ultimately we'd use those two values to come together for a KFS, such that our actual value of shear that we care about is KFS times our computed torque. Again, in this case, with this being the smaller diameter, our actual one would be KFS times 16 torque over pi d cubed for a solid round shaft. Now, if we had the situation where we had that shaft in both bending, this is the bending moment, and in torque, so we had the torque being taken on and off the shaft, we would still look at the same location, and we would still calculate a normal stress due to bending, and we would calculate a shear stress due to torsion, and we would multiply those times their respective Kf for bending and Kfs for shear, as if we were ignoring the contribution of the other part to come up with our actual stress and our actual shear that we will use for the rest of our failure computations. So we can do this in parts, and we will come up with accurate estimates of those values. Well, that'll about do it for this video. Until next time.